next topic I'm going to talk about, this will be a little shorter than the last talk, is on defining a study population and calculating a sample size. These can be pretty dense topics, especially the calculating sample size part. It gets into a bit of math, and it gets into understanding some of the distributions that we talked about before. And I'm going to try to keep it as much as I can kind of high level and conceptual, so that you hopefully walk away from the talk understanding why sample size is important, what are the components of a sample size calculation, how is sample size different from power, and how are they related. You've probably heard many of these terms, and just what you should be thinking about as you design a study with respect to sample size and power, without getting too into math or how to actually do the sample size calculation. Because truth be told, if you haven't been trained to do the calculation rigorously and understand all the little nuances of it, doing the calculation yourself can be a little dangerous, because you wind up sort of getting the wrong answer. And you have a great group of biostatisticians available in Madurai to help with these kinds of things, and and certainly lots of resources. And I'm happy to take other questions or get into some of the nuances as best I can if you guys have other queries. But like I said, I'll keep it sort of high level for most of this talk. So we'll talk about study population, which is really important to understand how we define a study population, because that's the population from which we sample. So that kind of precedes any conversation about sample size. Again, we'll talk about why we're going to worry about sample size. We'll distinguish between sample size and power. And we may talk a little bit about minimally important differences, but we'll see if we have time to get into that. So we're never, or very rarely, going to sample an entire population. So when we talk about a population, we're talking about all patients in Aravind Pondicherry, all people in Pondicherry, all people in Tamil Nadu, all people in India. We're talking about big groups of people, and it's rarely feasible to get every individual from that big group of people to study, right? So we hope that we're able to acquire a sample from that big group of people, and we refer to that big group of people as our sample frame, right? So we define it as women in Tamil Nadu. That might be a sample frame. Or women over age 65 in Tamil Nadu. That would be a sample frame. And we sample from that group. And there are different ways of sampling from that group, but ultimately we hope that we have a pretty random, pretty representative sample, so that we can make inferences or learn something about what's going on in the larger population. Because what we really care is not how the 85 women over age 65 from Tamil Nadu's eyes behave. We care about how eyes behave in general for women over age 65 in Tamil Nadu. So we want to make inferences, and we require some sort of random or not systematically different sample, right? We don't want our sample to be systematically different from the larger population. So it's important to think about this and think about how we're going to define both the population of interest, but also pull from that population of interest for our study. So what that means is that the study sample should be generalizable to our target population. And one of the terms we use when we talk about generalizability is also external validity. That is, your study should be external, beyond its own borders, so that you can say something bigger about the world. It also needs to be big enough that we can actually detect an association, right? If we have 4 people in our study, it's unlikely that even if something's going on, and even if these 4 people are pretty representative, it's unlikely we'll actually be able to detect what's going on. And we'll talk a little bit more about that. So why should we worry about sample size? Well, for one, if we were to recruit every woman over age 65, just to stick with that, with that line of thought, in Tamil Nadu, we'd likely be overpowered, and we'll talk about power in a minute, for whatever we're trying to do. And this wastes money. It's very expensive. It wastes time. And then the second bullet point, the last bullet point here, it may show us significant associations that aren't clinically significant. And we'll talk more about that as well. We also want to avoid the impossible, right? If we're underpowered, it's unlikely that we're going to detect a difference even if one exists, right? You may have discovered some new treatment that's really, really important for keratoconus, but if you only have 7 people in your study, you might not actually detect the effect of that treatment if you're underpowered. And what that means then is that your new treatment might be discarded as not useful, not efficacious, even though it might be groundbreaking and really important. Um, and this all translates into hypothesis testing. That is your t-test, your chi-squared test, your regression models, in that it helps us to state with a certain degree of confidence that the association we're looking at or the treatment effect that we're looking at is likely to be real. And again, that's something we'll talk more about. So I'm going to get into a little more technical, a little more in the way of technical details here. Is that a pointer? Yeah. So there are essentially, if we have some sort of, we have some study that we're doing, right? Say we're looking for the association between, I'll take one of the groups that I'm working with here of Aravind faculty who are looking at an association between vernal keratoconjunctivitis and keratoconus, right? So perhaps, well, this is structured as treatment. Maybe we should go with a treatment analogy. Let's say gonioscopic assisted transluminal trabeculotomy, right? GAT, a new procedure for open angle glaucoma. We want to know if it works, if it decreases pressure, and if it decreases progression of glaucoma. So there's a reality, and that is unknown. That's what we wish we knew, but we can't really know what's going on in everybody that's ever had GAT, or the whole population if they were to all who need it have GAT, right? That's reality. And then there's the statistical result. There's what happened in our sample, right? We had a sample of 50 people that underwent GAT. What happened? So there are four possibilities. One is we think the treatment worked based on what we found in our sample, and it really does work, right? So our result is in line with reality. Another possibility is that we found it didn't work, and really it doesn't work. So again, unfortunately, but in line with reality. Yet a third possibility is that we found that the treatment works, but in fact it really doesn't work. So we now think we have a new treatment, but that treatment's not actually effective. The fourth possibility is that we think the treatment didn't work, but really it's a useful treatment. And so we didn't detect something that's really there. We now don't have this treatment available to us because we've written it off as not effective, right? So these two errors, the false positive and the false negative, are respectively referred to as type 1 error, type 2 error, and the Greek letters that are used to refer to these are alpha and beta. This, alpha, is our p-value. So we actually pick, before we do the study, what our p-value or alpha error is going to be. We're going to accept 5% type 1 error is pretty common. And we'll talk a little more about that. So with type 1 and type 2 errors, sometimes it's good to go to sort of an easy to understand example to understand what a false positive and false negative or type 1, type 2 error are. I think you can all understand that both of these are wrong for different reasons, right? But there's a differential cost to type 1 and type 2 errors. What I mean by cost depends on your study, right? There are some studies in which you really want to make it sure that you're not going to commit a type 1 error, and you're willing to accept more type 2 errors. And the opposite may be true, depending on certain studies. So we can imagine that if there were a drug that had a lot of bad side effects, but we thought maybe it was really useful, we wouldn't want to come up with the conclusion that it's useful if it's really not, because we'd be putting all these side effects on people when in fact the drug's not useful, right? So that would be a type 1 error if we falsely say the drug's useful, but it's not, and it has really bad side effects. That would be a costly type 1 error to make. A costly type 2 error to make might be if there was some new life-saving cancer drug, and our study showed it wasn't effective when in reality it's life-saving. So that would be a very costly type 2 error to make. So depending on what you're studying, you have to kind of decide, I'm willing to accept a little more of one type of error, but not the other. And they really do sort of move in opposite directions. So if you want to be tighter on one type of error, you have to be a little looser with the other. And as I said, the tolerance for the two types of errors is really built into your study design and your sample design. So when we get down to calculating a sample size and talking about sample size analyses, there are really four key components. The first one is effect size. So effect size kind of comes, I think the easiest way to think about effect size is to go back to one of those analogies that I talked about in the last lecture. So if we imagine that we want to detect an increase in acceptance of referrals from our eye camps, right? We detect glaucoma and diabetic retinopathy. Only half the people we detect suspicion of those diseases and show up back here at the hospital. We want to move that bar from 50% to 70% because we think 20% is a reasonable effect size worth measuring. So that would be an effect size, right? It's easier to detect big effect sizes than small effect sizes. And that makes sense. It's sort of like searching for something in a drawer, right? If you're searching for a big object, well, it's easy to find, but if you're looking for a little paperclip, it might be tough to find, right? It's easy to find big effect sizes compared to small effect sizes. There's the error rate. That's alpha. That's the type 1 error rate. So how many of those false results, right, where we think that there is a positive result, but there's really not, how many of those false positives are we willing to accept? That's our alpha. Statistical power is a little more complicated. Statistical power we'll get into in a bit more detail in a few minutes, but it's 1 minus the false negative rate, or the beta rate. So we oftentimes will set statistical power at 80 to 90%, and so that means our beta, we're willing to accept somewhere around a 10 to 20% false negative rate. That is, we think there's no effect, but really there is. Because in most situations, we're more tolerant of throwing out a result and saying there was nothing there than we are of accepting a result that's not actually true and telling the world that it's true, right? And then sample size is, in most cases when we use these formulas containing these 4 components, the thing that we're solving for. We want to know how many people do we need in our study in order to have a defined power to detect a certain effect size with a certain error rate. So a few more reasons that we should care about sample size and worry about it when we're designing our study. It improves your research design. If you start to think about sample size, you start to think about different aspects of how you're going to design your study to get that many people, how you're going to, whether you're more tolerant of type 1 or type 2 errors, and also some of the pitfalls to having too big or too small of a sample size. It also helps you to plan your statistical analyses in advance because you're typically powering yourself based on a certain statistical test that you might be doing. There's different sample size formulas for different statistical tests. So you wind up talking to your biostatistician, thinking about the best way to analyze your data. It also, if you're looking for funding, improves your chances because reviewers and funders, they want to see that you're going to have enough people in your study to find an effect, if one is there, that you can actually recruit that number of participants into your study. It strengthens your data analysis section, and it shows that you're involving a statistician. These are all good things when it comes to reviewing a grant proposal, or a paper for that matter. So then, what exactly is sample size? I'm kind of getting to the essence of this whole talk. Well, it's the number of participants needed to have adequate power, and we'll unpack that word in just a second, to detect a certain difference. A 20% increase in acceptance of referrals might be the difference, and we want to have 80% power to detect that, right? So really, sample size and power are kind of 2 sides of the same coin, 2 ways of viewing the same question. When we do the sort of math problem to solve for sample size, we could do it a different way. We could say, I only have access to 300 patients, 300 participants. How much power will I have to detect a 20% difference if all I have is 300 patients? And in some cases, that's going to be the case, right? We're limited by either our resources or just by, sometimes when it's a rare disease, the number of people with a certain condition. And so we want to know how much power we'll have given that known sample size. So 2 sides of the same coin, really. I think it's more or less what I just said. So when we look at effect size, this is what I was talking about before, big effect size versus small effect size. So we can imagine that these are 2 groups that we're going to compare, right? The red and the blue. I know it's tough to kind of see a little tough to see the colors there, but the red and the blue, let's imagine, are 2 different groups. And we want to compare, we want to know if there's a difference between these groups. We can think very simply, is there a difference in height between men and women, right? So we have a distribution of men's heights, we have a distribution of women's heights. There's a reasonably large difference between the 2. It's going to be pretty easy to detect that on a population level, although not on an individual level, on a population level, there's a difference. Let's imagine, though, that there are 2 things that are the difference is maybe a little bit smaller. Well, it's going to be more difficult to discern that difference statistically. It's like finding the small thing, the paperclip in the drawer. when the effect size is small compared to that larger one. So the degree of overlap in those curves is going to depend not only on the difference in means, but also on the variance of the measurement. So going back to that analogy of finding something in a drawer, is it easier to find something in a drawer that's cluttered or that's pretty well organized and clean? So the cluttered drawer is when you have a big standard deviation, big variance, big standard error in your measurements. It's hard to find a difference. The clean drawer, where it's easy to find something, is when your standard deviation, your standard error is very tight. Right? It makes it easier to find something in a drawer. It makes it easier to detect a difference between two groups as well. So you have to keep both of these things in mind, and oftentimes they'll also play into the sample size calculation. However, we don't actually know what the effect size is for a given sample, right? If we knew that, if we imagine two different populations, we don't actually know until we study it the difference in average height between men and women. If we knew, we wouldn't have to study it, right? So oftentimes in a sample size calculation, where we're going to compare, let's say, two means, we have to kind of take a guess. And a guess might be based on expert opinion, some prior studies, maybe in another setting, or going back to the analogy we talked about with the ICAMPs and increasing referral rates, it might have to do with the smallest difference that you want to detect. You might say, I don't really care if I can increase acceptance rate by 5%. I only care about 15% or 20%. So that's an acceptable way also to decide on your effect size. And as we've kind of beat home here, detecting a smaller effect size is going to require a larger sample. So I think this curve, although fairly complex at first glance, is a nice way of describing some of the relationships between these entities like effect size, sample size, power. So what this is showing, the graph along the x-axis we have effect size. Right in the middle, there's an effect of 0, a delta of 0, no difference between the two groups. Over here, we have a big negative effect. Over here, we have a big positive effect, right? Because the effect can go in either direction. Maybe men are taller than women. Maybe women are taller than men. We don't know. We haven't studied it yet, right? So we say two tails that we're testing. And then along the y-axis here, we have power. So maximum power being 1, not really realistic. We don't really ever attain power of 1. But maybe up here we're at a power of 90%. What these two curves are showing, this is a large sample, this is a small sample, is a few things. Number one, when the delta is 0, when there's no effect size, we have no power. You can't detect an effect if there's no effect there, right? It also shows that at all other effect sizes, be them small effect sizes or large effect sizes, a larger sample is going to give us more power. All right, so that's kind of what this is illustrating. And if we're able to detect the effect at this point, at this point, at this point, at any point along there, then we're going to reject our null hypothesis. So that alpha of 0.05, which translates ultimately to a p-value of 0.05, is kind of a common accepted threshold that we use in many situations, although as we talked about, when we want to be more accepting, say, of type 1 errors, we might relax that a little bit, or less accepting, we might even make it 0.01, 1%. And what this means is that if we do 100 studies, 5 times we might find a result that doesn't really exist. For greater certainty, we can reduce that to 0.01, but that's going to change our sample size calculation and change implications for the power curve as well. Oftentimes for statistical power, we go with 80 or 90%. Remember, this is 1 minus beta. So if power is 80%, beta or a type 2 error rate is 20%. And that means 20 out of 100 times we're going to miss a result that's really there. But we're probably willing to take that because we'd rather sort of throw that out than be reporting results that aren't real or are type 1 error in most cases. So we can always increase our power to reduce the chance of missing a result, to reduce our type 2 error. As you can see, these are related by the 1 minus beta equation. But that smaller beta or larger power is going to require that we increase sample size. And we saw that before when we looked at the relationship between sample size and power just a minute ago on those curves. I'm going to stop here for a second. Any questions? I know it's a little confusing. No? Questions? No? So, as we said at the beginning, oftentimes we make some assumptions, 80% power, 5% alpha, we want to detect a 20% effect, and we're solving for sample size. However, it can be fixed, and power may be the unknown. A bigger sample may get us closer to the truth, right? At the beginning, we talked about sampling from our target population. So if we're able to sample more people from our target population, in many cases, we're more likely to approximate an actual random sampling of those folks. With a small sample, right, you can imagine if I talk to 2 people in this room about today's workshop, they might both say, oh, it was great, it was like the best thing I ever went to. But then if I actually talk to everybody in the room, I might get some different answers. And so a small sample might not really be representative, but as it gets bigger and bigger, 4 people, 8 people, 12 people, I'm going to get closer to that truth, right? So then if we care about truth and we don't want to commit type 1 errors, we don't want to commit type 2 errors in an ideal world, why don't we just set alpha and beta to be 0? 100% power, no type 1 errors. Well, we can't. We can't. It would require an infinitely large sample size to do so. And as a result, to accept more or to prevent more false positives, let's say, alpha, you have to accept more false negatives. They're inversely related to one another. And you can kind of think about that with a real world example, and you'll see kind of how, to gain on one, you have to give on the other. So if we think about comparing 2 means, I think this is the easiest way to think about sample size, because it's something we do in our heads all the time, sort of roughly, right? We can think again about this comparing mean heights of men and women. If we let alpha equal 0.05, we're willing to accept 5% type 1 errors, 90% power, so that's 10% type 2 errors, and we have a 2-sided test because we don't know, right? Are men going to be taller? Are women going to be taller? We want to allow for both of those possibilities, right? If we're only going to allow for one of the possibilities, we call it a 1-sided test. It requires more power to look for both those possibilities than just one of them. What we see, just kind of illustrating here, is that as effect size and variance, or standard deviation, changes, so we're going to calculate our effect size as the difference, or delta, over the standard deviation. So 0.25 is going to be a small effect size, 2 is going to be a huge effect size. What we find is that to detect that tiny effect size, we need a pretty big group. As the effect size gets bigger and bigger, the number that we need to detect that effect size, given these parameters, goes down. And that makes some sense, right? It's easy to detect a big difference. If all men were, 2 meters tall and all women were 1.5 meters tall, that's a big difference that we'd really be able to detect quite easily, especially if the standard deviation were very big. Of course, that's not the case, and the standard deviation is much bigger, and so our effect size winds up being, somewhere perhaps in the middle of the table, right? But we can imagine that we could get down here if those curves were far separated and tight. So there's a sample size formula for every test, whether it's a chi-squared test, a t-test, a Wilcoxon test. And it's not important to know all of those sample size formulas. I don't know if anybody knows all of those sample size formulas. There's software that can calculate it. You have biostatisticians that can help with that. We can look at one formula, and I'm not going to spend a lot of time going through the formula. I don't think that's useful here. But we can see just that every one of these components that we've talked about factors into the formula, right? So we've arranged the formula in this case such that we're solving for the number that we need in each group to look for a difference between 2 means. And it includes our standard deviation. It's going to include our alpha. It's going to include our beta. And it's going to include the difference that we want to detect between the groups. Right? So all the things we've been talking about factor into the equation. So, one of the problems that we see sometimes in studies is even being overpowered, right? We typically think about the problem of underpowering, in that we're not going to have enough patients, well, maybe not at Aravind, but we think about the problem of underpowering. We're not going to have enough patients or participants for a certain study. But there's a problem of overpowering too sometimes. When we overpower a study, we're likely to detect really tiny differences as the study gets bigger and bigger and bigger. What that means is that we might detect differences that exist in the statistics but don't really have much meaning, right? We might be able to detect something totally nonsensical, but it has no clinical relevance. So it's important to bear in mind that there is potentially a problem with having a lot of power if we're going to look at lots of different associations. If we're theory-driven and we know a priori beforehand what our hypothesis is, what we're looking for, and we test it with a large sample, that's probably fine because you've staked a claim before doing the study that this is what I'm looking for, and now you have a very large sample to look for it. On the other hand, in many studies with large data or big data, as we say, and this big data can come from medical claims for an entire country, or can come from a survey that's representative of all of India, or can come from any number of very large databases that can have hundreds of thousands or even millions of data points. We can find all sorts of associations. So we need to be very theory and very hypothesis driven if we're going to use big data. Statistical significance, as I've been saying, doesn't equal clinical significance. Just because you find the association doesn't mean it matters for your patients or is important for them. But statistical insignificance doesn't necessarily equal clinical insignificance either. And I left it out. There was a slide that I had thought about putting in, and it was this really great quote from an article published in Ophthalmology not long ago. It was 2015, 2016, just a couple years ago. And in one sentence, the authors actually said there was a difference between two graders on a particular entity they were grading, and they said p equals 0.03 or something like that. And then they said there was also a difference in the mean, I'm blanking exactly, but like on the mean percentage, the mean percent growth in the corneal ulcers that they were grading, let's say. And they said 15% versus 25%, p equals 0.3, right? So over 0.05, typical significance threshold. And the numbers were different, and they claimed a significant difference, even though their statistical test showed a non-significant difference. And so, I don't know if the authors in that case were getting at this idea of statistical insignificance but clinical significance. But we have to be very careful about how we portray our statistics, both in terms of claiming significance when it's not there clinically, but also in terms of things that might be clinically significant, even if statistically they're not. So we have to be careful kind of on both sides of the coin. That was sort of a big, broad overview, and I know it was a fairly quick talk.
Why does the overpowered study have this problem? Why do you think that it is having this problem of statistical significance that it is not clinically significant? Because the sample size from where they have drawn is not
well. So it's not that it always has this problem. In many cases it doesn't, right? So if we look at that study of Dr. Hari Priya's 2 million patients who received moxifloxacin as endophthalmitis prophylaxis, she didn't go into the study saying, I wonder what moxifloxacin would do if I injected it during cataract surgery, right? She went into it saying, my hypothesis is that by injecting moxifloxacin, we're going to see a lower incidence of endophthalmitis in our cataract patients, right? Theory-driven and very specific hypothesis. So big sample size, great for a couple of reasons. One, it was theory-driven, but two, it's a rare event. So especially for rare events, we need a big sample size, all right? However, the big sample size becomes problematic. Let's imagine that we're looking at a huge database. There's a study that's being conducted right now in India. It's kind of an exciting study. It's called LASI, the Longitudinal Aging Study of India. So they're surveying people from all over the country. It's 20 some odd thousand people, and they're representative actually of all states in India and all older adults in India. So it's a hugely important and very big study, right? So we have 20 some odd thousand data points in the study. And when we weight those data points, they're actually representative of the over 1 billion people in India. So we could use that data to look for some very non-theory driven association. You know, maybe you want to know, are men more likely than women to, I don't know, you pick something.
To get diabetic retinopathy?
To what?
Get diabetic retinopathy?
Sure. Okay, so let's say there's no theory there, right? Like we just think, yeah, maybe men are more likely than women to get diabetic retinopathy. It's very likely that you'll find a difference because your sample size is so big that it's very likely that your variance is very small. There's a smaller standard deviation, and that you're powered to detect things that might not be clinically relevant, right? Or might not be clinically applicable or clinically even there. Your power has exceeded your power has gone up so much that your type 1 error has increased, right? Because remember, beta and alpha are inversely related. Other questions? That's a good question.
So what is the precision in sample size calculation? What is precision?
So precision is a slightly different measurement concept. Precision is, for example, you know, when we measure, let's say, intraocular pressure, is a good example. We can say somebody's intraocular pressure is between 10 and 20. Not very useful, right? We could say somebody's intraocular pressure is 15, getting more useful. We could say someone's intraocular pressure is 14.8326 if we had a way of measuring that, which of course we don't. And that would be a very precise measurement, right? It's no more accurate than saying it's between 10 and 20. That was entirely accurate because 14.826 or whatever number I gave you is between 10 and 20. But the 14.826 is much more precise. So that's the difference between precision and accuracy, which are important measurement concepts in a lot of study design. Yep.
The alpha value is p value which we take as 0.055%. So how do we arrive at a beta value 10%? How did we get that?
Yeah, so it's something you choose. It's something you decide based on your study. And if your beta value is 10%, 0.1, so therefore your power is 90%, right? Since power equals 1 minus beta, you need a bigger sample size than if your power were 20%. Or excuse me, if your beta were 20% and your power were 80%, right? So smaller beta, bigger power, bigger sample size. So you have to decide, well, one way to do it is you have to decide beforehand what your beta or your power is going to be to calculate a sample size. On the other hand, there are those situations where you know you only have access to 300 participants and you want to know what is your power going to be given that you want to detect a certain effect with this population of 300 patients that you have, right? And so that would be another way of arriving at beta given a known sample size. Does that make sense?
Sure, I'm getting it. So how do we arrive at beta based on the sample size?
Yeah. So it's if we have, right, so if we have an equation, right, the equation's set up right now so that we're solving for that, the term on the left, the number, right? But you could imagine if you did some fancy math real quick, you could solve instead for beta. All right? Yeah, exactly. So if you knew this quantity right here, you wouldn't need to solve for it, right? You would have a number there. You'd have a number in every other spot, and this would be your unknown quantity. And so you would put it on the left side and you would solve for beta. And that would be a way with a known sample size, known effect you want to detect, that you could calculate beta.
So we can approximately keep a sample size in mind and calculate the beta based on that.
That's a way of doing it, to say, you know, I have access to this many patients. How much power do I have? Or what is my type 2 error rate? Yeah. Other questions? These are great questions. Yeah.
Suppose I have already calculated the sample size is probably 100, but for whatsoever reasons I'm not able to reach 100 but reach now maybe 50.
Yeah.
And then I have results with significant p-values. Then is that study still significant or we need to reach 100 to?
Yeah. So it's significant. You found a significant value, right? Your p was less than 0.05, let's say. And just because you didn't reach your desired sample size doesn't mean you're going to to not find an effect, right? It's possible to detect an effect with a smaller sample size. Let's say if we back calculated power, your power was 50%, right? So that means there was a 50% chance that you weren't going to detect an effect if it was there, right? But you're lucky. You fell on the other side of the coin. There was a 50% chance you were going to detect it. So you didn't have much power, but you got lucky. So that's okay. Yeah. There's the caveat to that is that as the sample size gets smaller and smaller and smaller, we can start to violate some of the assumptions of our statistical tests, and I'll talk about that in my afternoon talk. Some of the assumptions that go into doing a t-test or a chi-squared test or building a regression model. So it depends a bit on your statistical tests, on your analysis plan, if 50 is going to be enough. So it's more than just how much power you have, but also on the test you're going to use. Other questions?
How the effect size is incorporated in this formula?
It's the delta down here. So it's this. So it's the smallest difference you want to detect. So going back to the analogy of height between men and women, right? You don't care if there's only a 4 centimeter difference. You want to detect it if there's a 10 centimeter difference, right? So you put your delta in here. And if you were to choose a smaller effect size, you want to be able to detect something as small as 1 centimeter difference between the two distributions of height. You're going to need a bigger sample size, right? And you can just kind of play with that in your head, right? As delta, as the difference gets bigger, right? Our denominator is bigger. We're dividing by a bigger number. Our sample size is going to get smaller. The value we're solving for right there is going to be a smaller value, right? Other questions? Those were all really great questions. Thank you guys for being interactive.